matrix factorization. Starting to record on air. Don't say anything not interesting, just say interesting stuff. So matrix factorization, what will I talk about? SVD, no. You're already supposed to know that. That was the preview. I will talk about what we're talking about. And then independent component analysis. That was that. I'm not heavily prepared to kill you with ICA, but I will try on NMF. With ICA, I will just do blackboarding the old style as well. NMF is a fun thing. Dictionary learning, another matrix factorization technique. Autoencoders. You can think of everything in this lecture a little bit as unsupervised learning, although more specifically, it is matrix factorization, and a lot of unsupervised learning, which is not clustering, is matrix factorization, although clustering often can be represented. So, and I'll give you some take-home points on what I mean in this lecture for you to remember or to take away from. So let's look at one shallow model, right? This is the same. What's on the screen is actually a graphical representation of this equation, expression. Two matrices are multiplied by another, or rather, if you go in this notation, well, the way it's written symmetrically, but you could say, well, depends on how you define W, but there will be a transpose either there or there. So this graphical representation, which is a little bit misleading, but the important part, each connection here simply represents an element in this matrix, in the W matrix or W transpose, regardless. Everything is connected to everything. It's a bipartite graph. Nothing is connected within the levels, say visible level, hidden level. Think of this just as words, just as labels. Don't think into meaning too much. I'm taking this picture from a representation that I drew for a restricted Boltzmann machine. That's where the names come from. But any matrix factorization or any matrix representation is like that. And although those V and H are vectors, we put together all of our V's, visible units, as data into a matrix, and we get a matrix. And a product of two matrices gives us another matrix. So you can think of it either graphically, as in this picture, and again, everything connected to everything, but imagine that the non-bolded edges are just zeros or very low value. And every method that I will talk about today is represented by this problem. And usually what we have, usually we will be working, if we use this notation, hidden, mixture, visible, usually we will be working with this. We, no. Right, so we have V, and we're looking to approximate V by a product of two matrices, or however many number of matrices, but usually two in the methods that we will talk about today. So let's start with the most difficult of all of the methods, I think, from today, but was the most easy exposition because I'm not going to go into much detail on independent component analysis. And I will use, I forgot what the slide style called, the textual slides. That's why I didn't record it. So cocktail party problem. In the independent component analysis is traced back to either to the 70s or to the 90s. and it comes from two different communities. Depending on which reviewer you get, everyone will claim that you're wrong. So if you don't mention both those communities arrived at the problem independently. One community in the 70s was looking for axes on which to project the data such that it doesn't simply end up in a lump of circular cloud of points as Gaussian, because back in the 70s and the people were just projecting the data into two-dimensional space, and mostly it was orthogonal projections. Most of the data would just end up as a lump, as a Gaussian lump of data on the piece of paper. So people started thinking about projection pursuit. Can we find directions in the data one by one in that high dimensional data, such that the data is not simply projected into orthogonal grid, but some non-orthogonal grid, and so on. So they were developing, and somehow most of people didn't know about that line of thought. Simultaneously, in the 90s, early 90s, late 80s, people started talking about the problem called blind source separation. What if we have a mixture of sources, and most, like, your central limit theorem, your lots of other results, most of the stuff that we measure is a mixture of stuff. We don't measure any kind of pure measurement signal directly. We usually measure mixtures. And blind source separation established or posed a problem. How can we extract the sources that were mixed somehow in any way? That's why, I will tell you about cocktail party. That's a specific way of mixing sources without any additional information. Is there a way? That's why blind. Is there a way to extract the sources that were later mixed somehow? So cocktail party is talking about a specific way of mixing sources. So if we have, cocktail party is very visual. That's why everyone is using it. So if we have microphones, pardon my dandelions or whatever, and we have speakers, and imagine that I drew enough smiley faces to match the number of my microphones. Just for simplicity, I have the same number of smiley faces as microphones. And when they speak, the signal ends up on each of the microphones. That is, each microphone measures each of the speakers. And we can represent our measurements at the microphones as our data. Yeah, too bad. As our data. Let's use notations. Call our speakers sources, and the matrix of coefficients that is used to add up the signals from each of the speaker at this particular microphone, is a mixing matrix. So that is our cocktail party problem. And cocktail party problem is successfully solved by humans. You can imagine that when you are in a large party and everyone is holding a small talk around you, you are able to maintain a small talk with the person that you're talking with while everyone around you is talking, but you're still able to separate the sound of the person who is talking to you. So easily understandable what I'm talking about, and as most of the analogies and models completely wrong. Cocktail party problem and ICA are unrelated. Independent component analysis is unable to solve cocktail party problem because it's freaking nonlinear mixture, because you have delays on those microphones. It's like everyone in the field is motivating independent component analysis with the cocktail party problem. But this equation here notice, assumes instantaneous mixtures, that the signals, the sources at the signal at each source, let me draw those signals. This is my S, and this is my A that I'm multiplying each row by a column here. The assumption here is that when this person is speaking, the signal from this person arrives at this microphone at the same time when it arrives at this microphone. So for real cocktail party problem with real physics with speech, this problem is wrongly set up. So like, I'm kind of giving you simultaneously two conflicting worldviews, right? Like in the school, they told you, oh, when you see this, no, division by zero is impossible, don't do that, or at least, I don't know, in elementary school or when they do that. And then suddenly they come to you and they say, oh, sorry, that's perfectly fine, don't worry. No, it's like you can divide by zero, you cannot. The same here, they're giving you didactically I'm giving you a wrong view, but you understand what is mixing, right? But in fact, in order for this mixture to happen, you need instantaneous mixtures. Luckily, we have electromagnetic waves that move with speed of light, and we can ignore on short distances the delays because they're so fast that we can even use quasi-static Maxwell equations, assuming there's no dynamics. Especially our heads are, unfortunately, are so small that the signals propagate instantly through it. So in brain imaging, in electroencephalography, EEG, I don't know why it started sensing my hand. In the EEG and fMRI and other signals that are practically like instantaneously combined on the sensors and propagate using electromagnetic phenomena, we can use independent component analysis. You see what I have there? Yes. So, well, at least we can. I didn't tell you anything much about independence yet, but at least you can see this problem on the screen. Imagine the cocktail party problem, but such that our sound goes with the speed of light. And then you will see that if we can decompose this matrix given X, if we can find both A and S, then we're done. But how can we find both A and S? There is a lot of ambiguity. We should put some constraint on either or both in order to find something, because as you know, 10 equals A plus B, or A times B. You can have any A, any B, or like in our case, it's A times B, right? There are many possible solutions. So independent component analysis is a problem. So larger umbrella problem is blind source separation. But then we minimize the problem domain. In many books, it's called, I was browsing through the deep learning book, and it's called an algorithm. Independent component analysis is not an algorithm. It's a class of problems. It's a smaller class than blind source separation, because blind source separation combines all other stuff besides independence. But independent component analysis says, let's assume that those speakers are independent from each other. So what does independent mean mathematically? We assume that independence means if we have two speakers, then their joint speaker X and speaker Y, then their joint probability is a product of their marginals. So that's what statistical independence means. There is also linear algebra independence, orthogonality. Don't confuse them. You can say,
this would be a very strange conversation if everyone's talking doesn't relate to one another in any way.
Yeah,
cocktail
well,
party
but
would be.
surprisingly, yeah, if you if you impose this assumption so that it holds 100%, then yes, it's like everyone ignores everyone. There is no communication. But interestingly, if we maximize this, then like there is enough in the signal in the speech that makes it independent. Like for example, with this model, you can take musical sources, just songs, and well, they are independent in a sense, right? Because you just took those songs from different recordings and mixed them with linear mixture. You can demix them like almost perfectly, or even perfectly, if you don't add noise. With people, it will work as well, though, if we make sure that there are no delays.
I mean, it seems like the obvious thing is that people don't tend to talk over one another most of the time.
No. This does not matter. Yeah, this does not matter. Even if we talk over one another, there are other approaches to this case, to separation of people simultaneously talking. We
Well,
can.
it's just really counterintuitive that this would work. Like, is it just the representation of it that, like, I don't know. It seems like a very stupid assumption.
The dependence between the speakers, or the signals in the brain, is much lower than their own intrinsic signal, the independence. So you can maximize independence and say your dependence will get lost in the noise. And maximizing doesn't mean optimizing it totally, like making them completely independent. So okay, yeah, but you're right with those doubts, but they turns out to be, in practice, they are minor. And in practice, when we're using, well, and again, cocktail party is just a motivator for this problem. First of all, because of delays, the mixture is nonlinear. Then if we're talking about speech, there is even a more interesting problem called monaural speech separation, when you only have one microphone, which as humans we can do, but we have complicated language models involved as well, and all kind of higher level machinery to separate two people speaking. When we can separate with one ear plugged, we can separate a few people speaking simultaneously about their own stuff. Not, yes, you're right. When people converse, they don't speak together. Oh yeah, okay. While trying, I found the answer. The cocktail party, right? We assume that no one cares about each other, right? People just talk to in small groups or something. So you hear all of that, and they are indeed independent mostly. Again. Well, anyways, one type of independence is the statistical type of independence, when the joint is a product of marginals, or we can generalize it, right? Set of x's is a product of xi's. This is not raw. This is b, and this is an I. Don't confuse this with linear independence. Linear independence, yes, x transpose y is 0. They're orthogonal vectors, although there is a relation that basically, if you have Gaussian sources, if you have Gaussian random variables, then linear independence is leads to decorrelatedness. Remember how we computed covariance matrix, correlation matrix? It was x transpose x. That's how we estimated the covariance matrix when we collected our samples inside of the x transpose as rows. And
wait,
then
isn't linear independence just when they're not collinear? They don't have to be orthogonal. You just like the span of the two vectors spans the whole.
yes. But with these three, none of them are collinear, right? But one is extra, one is dependent. Any one. But usually when we think about orthogonality or full independence, right? Yeah, like you're right about the span, but then there is this the full orthogonality, and the full orthogonality is close to statistical independent, but only for Gaussian, for the distributions that go only up to second order moment, mean and variance. When for distributions that are described by just two statistics, this will be statistical independence. But it's not enough. There's more, like when you can be statistically dependent, still dependent with higher order moments, but independent in terms of correlation. Covariance matrix will be diagonal with some values on the diagonal. So ICA works with, or at least wants to push and assume independence that is more fundamental than decorrelation. So there is a difference. Why I'm saying that there is a difference that plays a functional role in independent component analysis and further between decorrelation. So let's talk about this. So when we used PCA and when we used KL transform and SVD and all of kind of diagonal, well, they're all the same, diagonalization methods, we took our data and then diagonalized it by finding, that's back to homework, by the way, and a question from someone. So our KL transform tells us, take W transpose the set of all of your eigenvectors, orthonormal set, so orthogonal matrix, everything is normalized to 1, and multiply by your data. That when you take an orthogonal matrix and multiply by anything or any vector, all you do is rotation. It doesn't change the length, it just rotates. So we would go from this to that, like a rotation. But then if we also took our eigenvalues, basically when we invert our eigenvalue matrix, we divide each eigenvalue, we invert it 1 over each eigenvalue. Basically what we're doing, we're turning our data into a circle, normalizing each of the new rotated axes to 1, or yes, to 1. So you have a unit circle, and this process is called widening, because your data becomes like there is no preference in any direction. It's decorrelated or widened, because white noise is the noise where every frequency is present. So in here, in the circle data, there is no preference for any linear direction. Like now, once you have a circle, you cannot diagonalize it, or effectively anything diagonalizes the sphere, actually, or a ball of data. And of course, what I mean by 1 is the variance. The data could be still anywhere up to infinity. So that's widening. Imagine like the problems still could be there. Imagine two of us are speaking and we're speaking independently, and this is person 1 and this is person 2. If we plot them on the axis of person 1 versus person 2, we get some signal here and some signal here. So now I take a mixing matrix and I mix these two, and I will get something like that, a linear mixture of those two signals. So now if I apply PCA, and even if I de-widen it, what I will get is I will find the major principal axis of the red data. And then I will rescale it so it's sort of circular. That's maximal what PCA can do, principal component analysis. KL transform, another matrix factorization technique that we already covered. But ICA will actually find this axis. And the goal of ICA is to find those axes that are still spanning the space, but are not orthogonal anymore. The independence of the sources is the guiding principle, or at least declared. And there are, so now, and this is all still just definition of a problem, not definition of how, right? Not definition of an algorithm. It's just, okay, well, we do this by using the algorithm, but by using or relying on independence, but how do we actually do that? So first, let's talk about ambiguities. Well, after you take those red, well, let me give you another example first about PCA. Let's take our data sampled, again, this P1, P2. And if the data is sampled, like you plot it against each other and you get a cube, or a square, or a hypercube for multiple sources, then we mix it, and our mixture will give us some kind of, I don't know, parallelepiped mixture. This is mixture. How do we get the mixture? We take P1, P2, and this will be like sample 1, sample 2, and we apply a 4x4 2x2 matrix, and we'll get this mixture, and we plot again this new coordinates. So if we apply PCA, PCA will first find the major axis of variance, and then widen. So after it will find those axes, here they are, the green axis. It'll make sure that the variance in all direction is the same. This is what PCA will find, and ICA will find something like that, closer to the regional data. Notice that this is still a mixture, and this is again the mixed signal. Ambiguities, well, there is a sign ambiguity multiplied, like you can multiply each one by -1, and you'll still get the same answer. So there is a sign ambiguity, there is a magnitude ambiguity. You can multiply A by 1 over lambda and multiply S by lambda, and you can still get the same X. There is a permutation ambiguity. You can permute the rows of S and you permute the columns of A, and you'll get the same X, those two. But there is another ambiguity with the Gaussian distribution. If you have a circular Gaussian distribution, then this ambiguity that I mentioned, that you can put your axis anywhere, anyhow. When your axes are orthogonal, you already have a problem because it's up to any rotation. When you are an ICA, where you can put any linearly independent basis, the number of possibilities is even larger. So ICA cannot work with Gaussian sources. PCA is built on the assumption of Gaussian sources. ICA cannot deal with them. It cannot disentangle. So now we are coming to how would you do it? Now you know that the sources are non-Gaussian. And in fact, if our speech is non-Gaussian, well, first of all, my speech is sparse because I pause to think about what to say next and things like that. I'm not just constantly emitting some kind of noise and sound. So any sparse signal, although it may seem to you like that, but of course it's not. Yeah, so identifiability leads us to some approaches. So one approach is called fast ICA, and yeah, the beauty of improvising gives me a chance not to go back too deep into details. So what fast ICA does, it observes the following. If we take a Gaussian, something like that looks like a Gaussian, probably from information theory, Gaussian is the highest, well, we'll need it next, but Gaussian is the highest entropy distribution for given variance. But also for if you measure moments, so first moment is our mean, then second moment is our variance, then the third one I believe is skewness, and the fourth moment is kurtosis. So what kurtosis measures for Gaussian, kurtosis is 3. For anything that is so-called sub-Gaussian, kurtosis is lower. Basically, the number of outliers on the tails is smaller than the Gaussian. It falls off, the tails of those peaky distributions fall off faster than the Gaussian does. And then there are super Gaussian distributions. Kurtosis is higher than 3. So what fast ICA does, it says, let's take our mixtures and let's find x equals a s. Okay. Usually what we do this, and then we say, okay, so let's modify parameters of the W. Let's start playing with our data, linearly transforming our data into S such that kurtosis is optimized, whatever we want, maximal kurtosis. Like we need to push it away from Gaussian. So the more non-Gaussian sources we get, the better. And so let's get our results away. Each one, then notice each one can be measured independently of each other. As long as each of them is non-Gaussian maximally as we can get, the result should be good. And the results are surprisingly good. Okay, but it's probably blasphemy in the scientific circles, but it never worked for us in brain imaging data. It's surprisingly good for toy examples, and it's blindingly fast, but somehow when you start working with brain imaging data, real data, it doesn't give interesting solutions. It doesn't convert to something that we can use, or it converges to suboptimal results. But it's fast, easy to understand. Relatively easy to understand, because the problem is choosing a non-linearity that would measure the kurtosis when you're doing optimization. So, but just some intuition. Another algorithm is based on a different principle, now with entropy. And this principle is called Infomax. Remember our initial figure where we had our visible units and hidden units, or input and output. Think of it as input and output. Think of it as if our output is the sources that we want to get, W is our demixing matrix now, because we are unmixing, well, I redefined all of the notation, X is V, S is H. So if that is the case, Infomax principle says that if our, and I envision a question, so we, from Jack, I guess, or anyone, what's the problem with maximizing mutual information between input and output? What would a degenerate solution be? For W. Okay, identity. So identity transform will maximize the information because they will be the same. But so ignoring identity or avoiding identity, Infomax principle tells us, let's maximize information. Let's set the W such that the information between input and output is maximized. We can decompose this information, mutual information. Well, mutual information in differential form is nothing but KL divergence of the joint distribution and product of the marginals. So we want to minimize KL divergence of this two, and we know that y is wx plus some noise, maybe. So this you can multiply the log through, and you can observe what happens. But basically, you have entropy of x and entropy of y minus conditional entropy of y given x, or cross entropy. Well, conditional actually. So this number or this entropy does not depend on W. This is like leftover, and all Infomax is trying to do to maximize mutual information between input and output is maximize the entropy of the result of the output of the sources. And just one last comment, the way it does it, we treat this matrix factorization, now some connection between, like, everything is connected back to the KL divergence, but Jack noted that already in one of the posts on Slack, and everything is connected with deep learning and all this. This is a single layer neural network. If you put a sigmoid unit here, logistic regression, right? If you put our logistic sigmoid unit, think about two nodes, two output nodes. Each one has a sigmoid unit. Sigmoid unit squishes the output to stay between 0 and 1. If we plot x and y on the output, well, I'm overloading. Let's say y1 and y2. If we plot them as y1 and y2 here, then sigmoid will not let them go outside of the 0 to 1 bounding box. Sigmoid keeps them in the bounding box. When we go from 2 units to multiple units, we're talking about keeping our output in a hypercube. And within a hypercube output, which one has highest entropy? The one that is spread around uniformly, the uniform distribution. For any bounded interval, uniform distribution has the highest entropy. For unbounded distribution with given variance, Gaussian has the highest entropy. So what Infomax is trying to do, it's trying to find an unmixing matrix such that the output is in the output is distributed as much uniformly as possible.
So one question, this expression I of xy is the mutual information here, right? And it looks like it's not symmetric between x and y, but then the one that you wrote down at the bottom looks like it is.
It is symmetric. You can rewrite it either which way.
So, I mean, okay, so it is symmetric at the top. So if
yeah. You can just rewrite it in different. You can
probability of y given x is equal to.
Yeah. You can just flip it. Yeah.
Oh, okay, and, it's not the probability; it's the I got you.
It's entropy. Yeah.
It's the entropy.
Yeah.
Oh yeah.
And
okay.
Yeah. With entropy, it's well, as you remember, right? Probability and the differential entropy, right?
So
And
this bottom is equal to I, the mutual information, or it's equal to the entropy of X given Y. This expression.
This is mutual information. This is not entropy. Okay, let's do the exercise. But I have a lot more to tell you about in this lecture. So, but let's try.
Okay.
So,
I mean, I can just look that up.
if you open up the log, right?
Yeah.
You will get negative entropy of the joint minus like, let me try. Do you still see my screen?
I mean, I can just look up I just don't know the definition for the entropy of X given Y, I guess. I can just Google that.
It's cross entropy.
Oh, okay.
Maximally. You're multiplying the joint by the log of the product, but then you have yeah.
Sorry.
Well, in any case, but the point of entropy, or the conditional entropy, yeah, it is called conditional entropy as well. But the point of conditional entropy is that this is the information in Y that does not depend on X. Oops, window is closed. Screen sharing has stopped. Next time this happens, please tell me. Desktop 3. But the point that, yeah, and I understand. I'm not going in a very detailed and sort of step by step, skipping lots of steps. Just trust me for now, but you can look it up later. Usually in my lectures, I try to show all the steps. But to maximize that, it's enough to maximize entropy of Y, given that Y is a linear function of X. And then you're dealing with random variable transformations here. So you need a Jacobian, your distribution of Y, if you remember, right? Your distribution of Y, how to express distribution of Y through the distribution of X. You need the Jacobian, I believe, divide by Jacobian, right? Something like that.
Just
Yeah.
linearizing.
Yeah. Well, no. This is from transformation of random variables. If one random variable is a function of another, and you know the distribution function of the original random variable, what will be the distribution of the result? This is an aside anyways. Turns out Infomax needs RW to be invertible because of this division by Jacobian, and RW ends up, yeah, like you end up with W inverse times probability of X, and then you'll get probability of Y. That what I was not gonna talk about anyways. But the point is, let's maximize the entropy of the output to maximize mutual information between X and Y, input and output. Infomax does that in just iterative batch manner, mini batch manner, maximize mutual informations in the mini batch. So take your X, map it into a hypercube, measure the entropy, see if it's uniformly maps into hypercube, and if it's not, keep going so that it maximizes it. Infomax gives very good results. Another approach could be much more simple, much more direct by like avoiding all the talk of entropy, neural networks, or rejection pursuit is maximum likelihood. And I'm putting it here just for completeness. Information theory book by David McKay that I put in the links to this class has a good exposition of this approach. If you'd like to know how you can compute, how you can solve ICA problem. ICA is a general problem. There are at least 3 algorithms. There are many more algorithms to solve independent component analysis. And it is still a linear problem. You're finding a matrix factorization, given your data, how you can decompose it in the product of 2 matrices, your mixing matrix and the sources. Sources are independent. Let's go to another problem just like that. On the surface, so morphologically, it's exactly the same. How one matrix is a product of 2 other matrices. In ICA, and especially with this condition of invertibility, you should have noticed that number of sources and number of measurements is the same. Otherwise, the matrix is not square and you cannot invert it. And the same was for PCA when we don't have to. In KL transform and in compression, in my examples in the notebook, we actually drop a lot of eigenvectors, but it is still a full rank transform, non-negative matrix factorization. So what it is, think about additive features. Anywhere you have additive features, like when you cannot subtract, when all of the features are positive, gene expressions, well, are like that. Arguably our facial features are like that, or at least we can use them. So if you have different eyes, noses, eyebrows, you can only add them like when you shine light through the film, right? Those are features additive. But they're unknown. You know they're additive, but all you have is the result. And you don't know which features were added together. Can you extract the features and their weights that will reconstruct any possible face? Think of human faces, think of different types of noses, but the algorithm doesn't know about noses. All it has is just pictures, all of the faces. Can we decompose? Let's define formally. I see some confused looks. Formally, it's easy. So one important is low rank. We don't want to have too many facial features. We want to only have like a few facial features and their different weight coefficients. So W, if our X let me think. So this dimension of W and H that gets multiplied is R, and R is small. That's what low rank means. We want to represent our data, and if we put our faces as columns of X, and we have many faces, we want to represent our data as a product of the, and I'll show you in the next picture, of the types of features and their weighting coefficients, such that everything, all of the 3 are non-negative. So 0 or higher. That's non-negative matrix factorization. How do we do that? Well, effectively, we are minimizing this objective, right? To satisfy this equality. So the Frobenius norm. And yeah, how can we do that? So and I'll show you an example later to understand what is W, what is H. So when we minimize this objective, just distance, squared error, Euclidean distance, think about it like that, if everything is a vector. If we think of X and the reconstruction just as a vector in some space, it's just Euclidean distance. We can differentiate with respect to W and differentiate with respect to H separately. And those are the results of, if we actually differentiate those two, that's what you will get. And we can just do classical solution, gradient descent. If our eta is just a single number, then this is simply a product. but I want learning rate. This is just a gradient descent learning rate. So h minus positive learning rate, but I'm assuming the learning rate can be negative as well or anything. I'm just doing the gradient descent for h here, and I'm assuming that I want learning rate to be different for each of the parameters, for each of the elements in h. I'm kind of optimizing them in parallel. That's why this element-wise Hadamard product. Another mostly forgotten trick, or at least not taught in elementary optimization theory, is this exponentiated gradient. We can element-wise multiply by e to the power of our gradient times the learning rate, and when the gradient gets to 0, we're just multiplying by 1, so nothing, like if the stuff stop changes. It's kind of an equivalent form. We're doing almost the same thing, or achieving almost the same thing, but I'm introducing here for you to introduce a novel, mind-blowing notion of optimization, that you don't have to add your gradients. You can multiply by some derivative of your gradient, like exponentiated gradient. So instead of doing steps additively, as here, we're still iterating, but we're iterating multiplicatively. When I first heard about it, that was like, wait, could we even do that? Why didn't no one tell me about it? It's just amazing. So now, okay, as you remember, the Leiden jar, the what is our logistic regression. Now, when we know what we want to do, we want to find such a multiplicative factor that we can just multiply by and converge to the solution. We can simply do the magic and find it. So if we set our learning rate magically, well, because we know what we want to achieve, right? That's what I mean by magically. It's not that we kind of stumbled upon it by some kind of roundabout way. Well, we know exactly what we want to achieve. We want to set our learning rate. If you take this learning rate, plug it here into your normal gradient updates, for h separately and for w separately, you will get to this expression. Do this exercise. It's just algebra, but it's interesting. Yes, just plug this into normal gradient descent. Division is element wise, and you will get learning rate is per each parameter. So the dimension of eta h is the same as h. The dimension of eta w is the same as w. And if you set the learning rate to this value, and notice I completely ignore the iteration index, but like those values here are at the previous iteration. All of the h's and w, you start with randomly initializing them to non-negative values, better away from 0, because the beauty of it, anything that is 0 in multiplicative updates stays 0. Any element in H that is 0, that is element-wise multiplied by anything, will stay 0. That's clear, right? Okay, and the same for W. But now, notice that we started with gradient descent, where we needed to set the learning rate. Then we just heuristically came up with a way to get rid of the summation and ended up with just product. But we also got rid of any hyperparameters. There is no learning rate anymore explicitly defined. The learning rate for each of the elements in H in NMF, in multiplicative updates of NMF, is dynamically changing with your updates. There are lots of tricks. If this goes to 0, anything here goes to 0, the algorithm blows up. What do? Fudge. the usual, right? Just add some protection so that it doesn't go fully to zero. But the algorithm is beautiful. It's very easy to code up in a couple of lines of MATLAB, Julia, Python, NumPy, anything you want. And it does find the factorization if you're careful with all of the sorts of numerical instabilities, and if you don't initialize incorrectly. Because yes, despite the simplicity, first time I implemented it, it didn't work. Because of course, one thing is a beautiful formula, another thing is reality. And if you don't know all of the tricks, how to not to get in trouble, you will get in trouble. So advantages: automatic non-negativity constraint satisfaction. Oh, well, if you start with non-negative H and W, non-negative times non-negative never gives you a negative number. So it's a constraint satisfaction problem, but we even forgot about it. It's given to us for free. Nice. Adaptive learning rate and no parameter setting, no hyperparameter setting. You still, I mean, we're estimating H and W. And it also minimizes the distance between these two expressions in the end. Interestingly, okay, let's, I think I need to see my next slide. Otherwise, I'm inventing the narrative here as I go. So let's take one column of X. It's a human face. Here it is. Then our features are W after the solution are those facial features, some eyebrows, well, sometimes with noses. And all you could do with those is add together by using those weights in H. And the weights are also non-negative. You're just adding them. You're not, PCA is canceling. PCA can add negative face to a positive face and cancel and create. And the rank is small, so you're using only a small number of those features, facial features, and you reconstruct. That's the reconstruction. That's how NMF works. You can also do the same with hyperspectral images and other kinds of data, people using ICA, NMF, sorry. Another advantage of NMF, you can show that NMF is basically by clustering. It simultaneously clusters in 2 dimensions, and people, you just need to permute the results correctly, and people are using that in genetics and other fields. Let's take that idea of matrix factorization a little bit further. So imagine that we want to be able to represent everything with just few numbers, few codes. If we have a large enough code book, if our typical faces code book, say, is large enough, then each face, we can only say like, okay, use those 3 features and represent this person. But for another person, use other 3 features. So sometimes non-overlapping. So the more the code book is, the sparser the coding, the fewer examples. In the extreme, I can just keep pictures of all of the faces, and I can just say, okay, this is the face. I just need one number and index into database. But dictionary learning says, can we take the data and learn those features where our alpha is a sparse vector? So we impose some sparsity on alpha by the constraint phi, L0 norm ideally, but we do L1 usually, sometimes LP norm, lots of approaches. I'm not gonna go into the actual approaches of how to train dictionary learning, but to give you intuition, which is important here, is that we can construct, unlike NMF, which was looking for low rank approximation, unlike PCA and ICA, which are doing full rank decomposition. Dictionary learning introduces another key idea if you haven't heard about it yet. It introduces over-complete representation. You have more than you need for linear independence. You don't care about linear independence anymore. It is you are giving more than you need to represent a point in n-dimensional space, because you want to represent a point now with fewer vectors. That's why it's instead, like, you know, in 2D, it's enough to represent everything. It's enough to have two vectors. But if we have tons and tons of vectors, maybe it's enough to have one point and the nearest vector on that point. That's kind of an intuition. When you go into multidimensional spaces, that's easy to understand, or at least makes more sense, because you can at least combine three linearly dependent bases. And here what they are, we can use it for denoising, of course. So our dictionary for this particular data would be like that, and dictionary is learned. So you will see an advantage. There are universal dictionaries, Fourier bases, cosine transforms in JPEG, wavelet transform in JPEG 2000. Those are universal. They're trying to be universally good without any expectation of what will come their way. Dictionary learning is, if you know what your data is, you'd rather learn the basis for your data. Notice those of you who are modern hippie boys or girls and playing with deep learning all the time. That's the mantra of deep learning. Let's learn everything from data. And deep learning didn't come up with that mantra. I mean, yeah, like this is like deep learning. Let's learn the basis from data. I mean, at least in this sense. Here's an example. Let's learn the basis from human faces. This is JPEG 2000. They're very good codecs or compressors. So this is the distance inside of KSVD is a method to do dictionary learning. This is the distance to the original, to the ground truth. The smaller, the better. And as you see, this is a reconstruction with exactly the same compression ratio. All of those methods, JPEG, JPEG 2000, PCA, they give the same compression. They have the same compression ratio, but the reconstruction looks quite differently. JPEG tries to be universal for all images. Look how better PCA is, because PCA was trained on this kind of data. PCA created eigenfaces, specific bases for that particular. That shouldn't be surprising now. But KSVD is even better, dictionary learning, because it created over-complete bases. So dictionary learning is a cool method. You should use it. It has a very interesting ideas, notions. I will go through the notions to remember to take away at the end.
I'm still a little bit confused about whether we're learning a basis or we're learning a huge set of vectors that's way more than a basis, and then like
over-complete basis.
Oh, but it's not okay.
It's called over-complete basis.
Okay, over-complete basis.
It's It's don't be too strict to definitions. As long as you understand. Yes, it's not a basis anymore. It's not linearly independent spanning. No. I mean, it is independent. Yes, I mean it's larger than the dimension of the space. But then the advantage is the compression, the bandwidth. Receiving party and transmitting party has a large dictionary now that they have to store, but the bandwidth is minimized, or at least how it could be, because you're sending only this and that, combine this few and you'll get what I mean.
And then is the number of vectors in your super basis or whatever is a hyperparameter.
Yeah. You decide how you want to do it. Yeah. Tons of difficulties there in optimization, of course. But one thing about NMF I didn't mention that will become important right now with autoencoders, which are surprisingly also nothing but matrix factorization. And even more, just I will tell that in a minute. Non-negative matrix factorization looks so we're minimizing this. This is interestingly looking problem. Looks like a quadratic convex problem, like convex optimization. If we were looking for just this matrix, let's call it x tilde. It is convex in x tilde, but we don't care about x tilde. We want the decomposition W and H. And once we want the decomposition of W and H, it is not a convex problem anymore. It's a convex in W separately and convex in H, but it is not convex in all of them. Look, this is a little bit surprising. All we do, like everything is linear. It's just two matrices multiplied together. And we're suddenly thrown away from convexity into an unknown world. What's going on? So autoencoders are even more interesting. So you have, this is important. Everything is linear. In autoencoders, original, everything is linear. Two matrices, low rank approximation. Encoder, you can take them the same matrices, doesn't matter. In this case, the same. So we have a new objective function, unlike all of the previous methods. And the objective, well, it's kind of the same, but still, we call it reconstruction error. In NMF, you can think reconstruction error. If you think x tilde is nothing but WH, that's your reconstruction error in NMF that we're minimizing. In autoencoders, we're also minimizing reconstruction error. X is what comes in, X prime is what comes out. You are projecting X to a lower dimension and then projecting it back to a higher dimension. You want to find projections such that the reconstruction is from the lower dimension is the best. Well, this is nothing but provably a PCA that this does SVD. I mean, they're identical. And when we'll get to the lectures on word vectors and GLOV, people were running around with word vectors as an example of triumph of deep learning, although it is A, shallow learning, B, it's not too different from SVD. It's actually a PCA and SVD as well. We'll talk about that later. So basically, this is our X prime, right? We take X, we multiply it by W, project here, and then we reconstruct it by W transpose. So that's autoencoder, objective function that we minimize. Encoder, decoder is right there. So in matrix factorizations, you can think you're doing the encoder decoder trick, but at least in autoencoder, you're doing it explicitly and you're calling it directly an autoencoder, like with encoder decoder that we use further. So the simple model, it is even simpler than NMF, no constraints, the same W, just transpose, it is not convex. Once you have a product of linear product of matrices, and you want to keep them separated and you start optimizing, you quickly fall out of the convexity and simple problems. Recently, somebody, Andrew Sachs, used that property to model deep learning by linear networks. It's exactly an interesting property, but if you multiply a bunch of linear matrices together, it is equivalent as a single matrix multiplication because you can just multiply them. You don't need this whole deep network. Or in autoencoder, if you multiply them together, this is just one single matrix transformed, low rank matrix, non-invertible, but still, why is it interesting to look at them separately? Well, because if it's a single matrix, you don't have that internal representation. In autoencoder, we're interested in this. Autoencoder does compression, and it is forced to do compression meaningfully because otherwise the reconstruction won't work. It is forced to leave only meaningful bits about the image in the compressed representation. Okay. Andrew Sachs, dynamics. Okay, let's skip all of that. So with autoencoder, since this is already a hard problem to optimize, why would we even limit ourselves to linear case? Let's add nonlinear and shallow two matrices. We can have deep autoencoders, nonlinear autoencoders, and they all are unsupervised models, although you're training them by backpropagation, by supervised technique, because you have an objective that you can measure, reconstruction error. So unsupervised, because you don't have to label anything. All you do is try to maximize the quality of the reconstruction or minimize the distance. So Jeff Hinton and Ruslan Salahuddinov has done this back in 2006 and published it in Science. That was an interesting publication because for years by 2006, support vector machines were dominating the landscape, and no one would ever in their right mind publish anything about neural networks. And suddenly the Science paper appears. What was the problem back, like a little bit of historical note, in 2006 and before 15 or 20 years? It was very hard to train the networks deeper than a couple of layers because the gradients would vanish and nothing would stay optimized. The suggestion in the Science paper was we can pre-train each layer using RBM and then train the autoencoder. Funnily, another group in Montreal, led by Yoshua Benjo, suggested to use the original autoencoder with reconstruction error to pre-train the layers. So basically, we take our autoencoder, split autoencoder in the small parts, and train them separately just so that this is an encoding and this is a decoding to reconstruct one from another. Well, anyways, now I've jumped quite away from matrix factorization. This is out of scope of this lecture. Just don't be afraid if you don't understand everything. But I think it's interesting and elementary how a simple matrix factorization model and problem can lead us to extensions that are interesting. So what they showed in this Science paper in 2006, that if you do two-dimensional projection on any of the two axes or principal vectors of PCA, you get something like that, an autoencoder, actually autoencoder compression, when your compression layer, the bottleneck is just two numbers, leads to a separation. It separates semantically the data without having any signal about the type of the data, just reconstruction error. That's fun. Another idea is from Yoshua Benjo's group is denoising autoencoder. So now what we do is, instead of simply reconstruction error, remember our reconstruction error was given X and given reconstructed X, how would you train it? How would you obtain the compression? What they did is they know the X, but what they entered into the system was X plus noise. And they expected, but they were judging the system against the true X. So this is a precursor of what's now is an interestingly developing and highly advertised and advocated for methods called self-supervised methods, when, again, it's like unsupervised, but you're adding some information that doesn't require any human labeling or intervention, and trying your model to it's like game playing, like kids developing brains will play games, modeling situations without actual situations, and we learn from them. So there's denoising thing. The task is given a noisy image, construct a denoised one is denoising autoencoder. Also an interesting idea. So take home points. Still have some time, but keep getting these calls. There are lots and lots of different interesting matrix factorization methods. The examples from sklearn, implemented ones, but sklearn is very conservative and they don't have many interesting methods implemented. And look how different they are. So PCA gives us kind of those smudge of faces. Those are eigenfaces. PCA Gaussian. Gaussian is close to Euclidean L2 norm. L2 norm spreads the energy, so that's why we get kind of non-sparse solutions. Fast ICA, a little more interesting, a little sparser, but still, you can add sparsity to PCA, and then you get the eyebrows and things like that. This is sparse NMF, I think. Yes, this is NMF. Dictionary learning, high frequency components. You need another advantage of PCA, so disadvantage of PCA, say in methods like that, is that your main components are low frequency, and then you need to get far in the tail to model those sharp edges like on the glasses. In dictionary learning, you can only take few already sharp components because they're not constrained by capturing as much variance as possible, and so they're that's why, by the way, they're better than JPEG and that kind of compression, the Fourier based on Fourier ideas, because Fourier tries to capture first low frequency components and then add higher frequency later because they're less informative, but not in this context. Well, k-means is an important component. Well, the important thing is missing here is vector quantization. We can also compress everything by prototypical faces. So instead of picking a constructed eigenphase, say like, okay, this face is a prototype. So vector quantization says, find me a cone of faces that kind of surrounding all possible faces, just few faces, such that you can, by convex combination of just those real faces, represent everything in the data set. I didn't talk about it at all, but that's an important kind of forgotten concept, but still it's good to know. NMF can automatically give you sparsity because non-negativity and sparsity are related, but not always. Often you need to enforce additional sparsity on NMF. And when you enforce additional sparsity on NMF, you get papers in iClear, as we did back in 2012, if I believe correctly. And I don't have enough time to talk about it, but basically interesting, now you have non-negativity that give you some sparsity, and then you can control the sparsity as a dial if you put additional constraint on, say, W, I believe, if you're saying that you want to minimize L1 norm of W together that, with minimizing the reconstruction error of NMF. Just a comment. So there's things to have in mind. That's your cheat sheet printed out and bring it with you on the next exam. Principal component analysis finds orthogonal axis of maximal variance, uses full rank transform, and can be used for compression when lower variance axes are dropped at reconstruction. What else? Frequently used to pre-process data, almost always. Even ICA requires that, and no one actually bothered to develop theory. Why would you need this? But anyways, independent component analysis, blind source separation problem, a sub-problem of the larger problem, still a problem. Finds linear transform that maximizes statistical independence of sources. Resulting basis is not orthogonal. As I said, it can capture other bases, but it's still full rank, full basis. Noise often independent of the rest of the data. So for example, we can, in the brain imaging, we can remove eye blinks and we can remove heartbeat and things like that because they are independent of what's going on in your brain, unless you're meditating on your eye blinks, I don't know, or heartbeat. So statistically independent, ICA is often used for denoising because you can clearly see, oh, this is not the signal I'm throwing away. It deconstructs the signal into separate source, and then you can reconstruct again a clear image, clear signal. Non-negative matrix factorization. Additive features lead to non-negative problem. Low rank approximation, multiplicative updates. Multiplicative updates is a beautiful idea. I don't know. I love it. Non-negativity leads to sparse solution. So dictionary learning, overcomplete dictionary, sparse representation of samples. Only few bases are involved in encoding in sample. I'm just repeating myself, but anyways, uses explicit sparsity constraint. Sparse MF does too, but let's say dictionary learning was the original way to do it. Questions? Those are very useful pre-processing techniques and very useful data exploration techniques. And well, of course, if you go into compression, information transmission, and all of that, without this, you usually don't do machine learning without those methods. At least classical machine learning, you wouldn't. But then deep learning approaches kind of trying to learn those things themselves. But if you don't understand how the methods of today's lecture work, then you don't understand what you're doing when you're applying deep learning. You're just a technician. So pay attention to the slides, these methods, and try to understand basic concepts. If you do need to do the algebra to understand them, do it.
I actually have a quick question.
Go ahead.
So sort of when you started talking about ICA, one of the things that I took away was the like PCA projection, where you just end up with this sort of blob, like overlapping blob, is sort of like a problem. Like your data is not separated in any way. It's all, and then of course, you just talked about autoencoders very briefly, and it was just one result, but the autoencoder gave us dimensionality reduction with this nice separation.
Well, that was non-linear autoencoder, though.
Yeah. Okay.
The linear autoencoder is nothing but PCA, provably.
Yeah.
This is non-linear autoencoder, so it can be a universal function approximator. It's probably can emulate stuff, but this is just PCA.
Yeah.
Linear autoencoder only doing PCA.
Yeah. Well,
not just shallow, but linear as well is important.
Yeah. Okay. So for the, I guess for, I mean, they're for the nonlinear autoencoder, I'm not applying this type of dimensionality reduction a lot, but at the same time, based upon what I just saw, I should be looking at nonlinear autoencoders a lot more.
Depends on what you're trying to do. Yeah, it's all depends on the goal.
Yeah. I guess that's a fair answer.
Well, reconstruction error is a take-home point, right? So you can use a reconstruction error to regularize your other objective, which people usually do. And autoencoder kind of explicitly enforces this into an idea space. Like you can see why and how it works. Many other methods use reconstruction error, but it's not so evident or clear. Okay. Any other questions? Okay, yay, I can get out finally. Thank you, and see you on Tuesday. I don't know what I'm going to talk about, but something interesting, I'm sure. Bye-bye.
Bye.